So it's 2:40. I don't know if you are ready to start. Looks not.
I think yes.
Yes?
Okay. If the other presenters are okay, we can start.
Okay. Natasha, are you here?
Yes,
yes.
Can you hear me?
Yes, so
perfect.
Thank you. So welcome to this second session, session 2, dedicated to SMARTI-EMBEDDED sensing systems for pavements. So this session is mainly linked to the multifunctional and automated pillars of the SMARTI project. In this session, we will have 4 presentations and then some time for questions at the end. The first presentation will be made by Natasha Bahrani Baloch on multifunctional road pavement monitoring system, WirelessBox. And Natasha did her PhD at University Gustave Eiffel. So Natasha, if you are ready, the floor is yours.
Thank you. Trying to share my screen.
So if you can stay in the 10 minutes presentation to keep the time.
I don't know if it's...
We see your screen. Yes.
Is it okay now? Oh. Can you see the screen?
Yes, it's okay.
Okay. So hello everyone, my name is Natasha Bahrani and today I'll be presenting about my work which is titled as WirelessBox, Multifunctional Road Monitoring System. So to introduce my work, it's mainly focusing on the pavement instrumentation, which can be an aid or a tool to help monitor the pavement and also assess the behavior of the pavement. So the objective is to have the evaluation of the performance of the asphalt concrete over different various environmental conditions as well as different traffic conditions over the time. And there's one parameter that we focused on was measuring the deflections, which can represent the bearing capacity of the pavement and overall strength of the field. And also the deflections can be used to back calculate the layer moduli of the pavement. And in our work, we have mainly used geophone and axiometers to measure the deflections. So, but traditionally, the pavement instrument monitoring or the assessment of the pavement was done through falling weight deflectometers and heavyweight deflectometers, which are still used. And the problem with these heavy vehicle deflectometers is that they are infrequent and they are done once or twice a year. And they require road closures and can be expensive. So the idea was to move towards embeddable sensors, which are geophones and axiometers in my work, and also anchor deflectometer, which are instrumented at the top layer of the pavement. And these sensors are installed on the top layer of the pavement and under the and are able to measure the pavement deflections on a moving load. So this is the general idea about my work. So this is the project outlines on what we have done in this work in this 3-year period. So first step was to have instrumentation testing. So to select the appropriate sensors and also test these sensors at different laboratory settings. And also to have the analysis of or the performance of these sensors on the X-rated pavement testing facility. Then the second step was to have the data treatment from the data received from these laboratory tests as well as the X-rated test. And the idea was to enhance the accuracy of the data, and also the geophones and accelerometers, as they were giving us information in terms of vertical velocity and vertical accelerations. These needed to be converted into vertical displacements. So it was important to treat and process the data which we received from the laboratory test as well as the accelerated test. The third step was to interpret the data that we received from the accelerated pavement testing facility. And the idea was to back calculate the layer moduli using the responses obtained from these sensors. And for this purpose, we used Alize and Elia pavement modeling software. And linear elastic approach was used, and an iterative method was used to find a good match between the measured as well as the calculated responses in order to obtain the back calculation of the modular. And the final stage was to apply the same processing technique that we developed at the second stage to the existing data that we received from the instrumented site at a highway. So the instrumented site was instrumented with the different geophones and the data acquisition system. And the data was processed and analyzed under the continuous monitoring under real-time traffic. So just to give you an overview about the instrumentation testing, the first step, which was to have or to analyze the modeling responses. So for that, we just used the pavement modeling software to analyze the responses. Second step was to have the laboratory test, which was done under a hydraulic table. So all our sensors were attached to the hydraulic table, and various speeds and various amplitudes were given to this, were inputted, and the responses were analyzed with respect to that. And the third step was to have the analysis on the APT, or the accelerated pavement. So the sensors were installed on the top layer of the asphalt concrete, and this was subjected, and the sensors were subjected to different speeds as well as different loads in order to analyze the responses in terms of reflection. But the second stage was to analyze and process the data. And here we have, we did some data filtering, as well as I mentioned before, the vertical accelerations and vertical velocities needed to be changed into vertical displacements. So we needed integration, and also we applied Hilbert transform in order to improve and enhance the shape of the signal. So here is one example of the signal that we received from geophone, as well as the reference sensor from the hydraulic table. And before the processing, the signal had an upward lift even after the integration, and was very different from what we wanted as a deflection signal. So after the processing here, we can see that the signal has significantly improved, and it's very much comparable to the reference sensor signal that we wanted. So the results obtained with the accelerated pavement testing facility. So the tests were conducted at different conditions, and so the dual wheel loading and 4.5 and 5.5 and 6.5 ton loads, and also under various various speed, which is 6 meters per second to 20 meters per second, and 11 lateral positions as well. So we had a lot of data under various conditions to analyze the responses of the pavement, and also compare the results with different sensors with each other, as well as the anchor deflectometer, which was supposedly to be more accurate than geophones as well as accelerometers. So here we have the results with the dual wheel fatigue also. Here we have example of 20 meters per second velocity, as well as the load of 65 kilonewtons. And the results are compared with anchor deflectometer, and they are very much comparable and very much close to what anchor deflectometer is representing. And we also analyzed the evolution of the results with the different speeds, with 6 meters per second to 20 meters per second, and we compared the results with the model response of ELISE as well as the ViscoRoot, which is viscoelastic software as well. And here we have the evaluation of the different speeds as well as the load. So just to give you an overview and the idea about how much the difference was between the measured and the model response. So for 64 kilonewton load, the difference was under 9%, and for 55 kilonewton load, the difference was under 7%, and for 65, it was 6%, which is very much acceptable in terms of the differences. So we conclude that the results were very encouraging and more accurate after the processing. So here we have to interpret the data which we received from the APT test. So using the sensor responses, we had to reverse calculate the layer moduli, and for this method and for this purpose, we used two methods, which is ELISE and ELIA. Both are linear elastic models, math softwares. So ELISE method, what it does is that it uses the deflections. Here we have an example of geophone signal. So what it does is that it uses the measured deflection, and it calculates the deflections obtained from the reference moduli. And what it does is that it alters the moduli of the pavement in order to best fit the measured as well as the calculated response, and the new moduli are the back calculated moduli of the pavement. Similarly, we have the ELIA pavement modeling software, but here the difference is that we are using the vertical velocity and vertical accelerations. Instead of changing them into vertical displacements, we are using it as vertical velocity and vertical accelerations. Here we have an example of geophone ion, and we have compared the measured responses with the initial calculated as well as then optimized the results in order to back calculate the moduli. And the results of this back calculation were also very realistic. So this also concludes that this is very encouraging for the back calculation of the layer moduli as well. The final step was to apply the processing techniques and the treatments of the data to the data which was instrumented with geophones, and the remote measurements were made from October 2014 to December 2016, and all the measurements were made with the new treatment procedures that were developed. And here we have just to summarize what we got is that we could understand the type of the loading from the data. We were also able to develop the reverse calculation of the moduli. We were able to tell the speed of the loading as well as the deflections variation over the time. And also the next step was to estimate the loads with the results as well. So this was just to give you an overview about the type of results or the type of interpretation we were able to do with the data received from the instrumented site. So to conclude, the development of we were able to develop the processing methods and calculate the deflections, which were applicable to all the sensors and two types of geophones and two types of accelerometers. And very high good results or very highly effective results were received with the indicated treatment. And also the validation of the results on the fatigue causal as well as the laboratory test, and then also applying the same type of treatment to the data site. Test site data was also very encouraging. The two back calculation methods were showing very realistic moduli, and implementation of the treatment to the instrumented data sites with geophones, we were also able to retrieve a lot of information about the evolution of the deflections with respect to temperature as well as time. We were able to characterize different types of traffic as well as the speed, and also we were able to estimate the loads of the vehicles as well. So this was just to conclude my work. Thank you so much.
Thank you, Natasha, for this very clear presentation. So stay connected in case there are some questions for you at the end of the session, and I'm sure there will be some.
Okay.
So yeah.
Thank you.
Thank you. Next presentation will be about smart economic and ecologic solutions for railway track beds. So this presentation will be made by Rufus. Sorry, I just checked exactly the presentation you sent to me. Rufus Adjetey Nii-Adjei. And sorry for the pronunciation, Rufus.
That's fine.
That's fine. Okay. So you are still doing your PhD at the University of Nottingham. You are currently in the final year PhD at the University of Nottingham, and you are continuing your research after SMARTI ETN toward the award of PhD Civil Engineering at the university. So, so the floor is yours. You can take the 10 minutes to present your work. And
all right. Thank you, Simon.
See you after.
Try and share my screen. Okay.
Yes, it's okay.
Okay, so thank you, Simon. My name is Rufus. As Simon said, my presentation today will be on smart economic and ecological solutions for railway track beds. My supervisors for the project are Prof. Nick Tom, Prof. Cordinary, Prof. Andrew Dawson, and then Davide Presti. So a general background of the project. In the UK, Network Rail is responsible for monitoring and maintaining and also renewing over 20,000 miles of track. And then monitoring this and maintaining this enormous network size is really, really expensive and also causes downtime to the network. But in the last 2 decades, there has been significant rise in population growth, causing greater traffic volumes due to mobility demands, business trades, and creating greater traffic volumes. And this has demanded minimal disruption for users. Climate change as well has affected or has posed a challenge to affect the performance and deterioration of our track rail infrastructure. And monitoring this can prove to be very costly. To ensure that modern railway tracks are sustainable in this long term and continue to provide users with safe journeys, as engineers, we are required to understand how the subgrade supports the track, and then we need to understand how the subgrade supports the track. It is also important that any deterioration in the pavement is noticed very quickly to allow early intervention, and then also to prevent non-sustainable activities such as excavation. Also, we must not forget that during these times, there has been development in intelligent transport systems as well. Wireless communications and sensor technologies have improved. And then within this environment, the project sought to develop new sensors to be able to harvest energy from the rail environment, to be able to monitor the condition of our railway network.
It looks your presentation is freezed. I don't know why. I don't know if I'm the only one in this case, but maybe you have to reshare or something like that.
Okay.
Share again? No?
Yeah, it's the same for everyone, I believe.
Yeah.
Do you see now?
Yes.
Okay. So hence we have the aims for the project to develop and deploy a low-cost self-powered sensor for continuous and autonomous sensing to monitor deformation in the subgrade under repeated load and harsh environmental conditions, and also to develop a sensor-specific data algorithm for pavement or the road track maintenance from the collected data from the sensor. The resilient strain on top of the subgrade will change with time due to traffic and environmental conditions, especially moisture. Hence, if we are able to keep record of this strain in the subgrade, we can be able to detect variety of faults in the pavement. For example, defects from drainage, which allows the subgrade to soften and hence affects the deterioration of the upper pavement layers or the track. For this, we were able to, the project has sought to develop this sensor, which could be embedded in the subgrade of the railway environment. Now, with this sensor, if they are embedded, we hope to be able to equip these sensors with wireless network, such that as the trains move over the track, the strains from or the stresses from the wheels of the rail from the vehicles will cause a signal to be picked from the sensors in the subgrade. Now, as these sensors are being picked, these sensors are self-powered, so it picks up the strains and then stores these strains in the cloud, which could be analyzed in a hub, or the data will be transferred and analyzed for prediction and maintenance scheduling. Now, as you mentioned rightly, I'm still continuing my PhD. So I joined the SMARTI project in the middle part in 2019. So far what has been done, as I've reviewed literature on the sensors, and these sensors have a potential to be equipped with wireless chip. And also, as I mentioned, the sensor is self-powered. For the experimental plan, we've had to calibrate these sensors in the lab. Most of the work that has been done so far has been in the lab and a few trials up. But then to be able to develop this sensor, we needed to use finite elements to see how the sensors behave under loading, and also to calibrate these sensors, we've been able to use a 4-point bending test equipment to see how environmental conditions such as frequency of loading, temperature, affect and voltage or strain that affects the output of the sensors. I'll go on and show on the lab approach and the use of the precision material unbound analyzer to pick up strains from subgrade materials, and then to evaluate the resilience modulus of those materials and compare with results from the gauge. And also I'll show a few images of field trials that has been done. Now, during the pandemic, it was very difficult to be able to work with the railway facility. So far, most of the trials that have been done, the field trials that have been done, have been in the pavement or the road network. Now, it's not a big deal to do that because the layer in which we embed these sensors are in the subbase or the subgrade, which is an unbound material, which is common in the pavement layers. So to begin with, to check the influence of strain and temperature and then frequency on the output of the transducers, we look for a material which flexes and has a similar modular as the transducers, about 3 gigapascals, and we subjected a beam of PVC beam to loading. We applied theoretical strains to it, and the output from the sensors the transducers were in voltage. So we could see that based on different temperatures, we have the response from the sensors or the response from the transducers according to various strains. Now we could realize that the strains here are very proportional to the voltages. And then also we checked the influence of frequency on the output of voltage. And you could see that at low frequencies, at a particular strain, at low frequencies, we have very low voltages. So it's very important for us to know that if we embed these sensors in a section of a track where we have very low frequency of loading, then we expect to have very low voltages compared to having a high frequency of loading. the next thing to do was to use finite element modeling to be able to predict the strains that we're going to experience in the transducer compared to the surrounding materials. So in here we have the gauge, the transducer, which you saw earlier in the 4-point bending on the dummy beam. And then this gauge has been cased with silicon and filler, which material which behaves more or less like an unbound material, which is very soft, a subgrade material which is very soft. From the finite element analysis, we have soil or subgrade material in a cylindrical shape, and then we have the sensor embedded in it, which we applied loading onto it and pick up the strains in the soil and also pick up strains in the transducer. So this is just some results from the finite element analysis. We have a plot of the rubber stiffnesses against microstrains, which is the strains from the piezo, so from the strains from the transducers. So what we did here was to see what type of stiffness of material would be adequate enough to give us enough strains that would be able to cause voltage output from the transducers. Realize that initially we had material, just silicone material, rubber material, and it was really very soft, so we had to modify it with filler to increase its stiffness so that we have enough strain from the piezo, because this piezoelectric transducer is very stiff. It's about 303 gigapascals compared to subgrade materials, which are very low in stiffness. Also, we look at the strain response per the rubber stiffnesses, and we realize that the higher the stiffness of the casing material, the better it is for us to have higher strains. Then we also did a comparison of the subgrade strain to the piezo strain, which helped us get a calibration factor. Based on this finite element modeling, we did use the resilient, we did use the PUMA, which is a precision unbound material analyzer, to be able to see how the subgrade materials resilient modulus changes, and if our sensor will be able to pick up these same strains or these same changes with time. So here we have the NanoAsphalt tester, and for our specimen we had a subgrade material. We had a clay, which looks more like a clay, and we had the sensor embedded at the bottom. So the dimensions of the specimen was 150 mil diameter and 150 mil in height. The sensor was 50 mil cube, so that was buried at the bottom and then was connected to a data acquisition system in the lab. Now the NanoAsphalt tester has a load cell LVDT, which measures the vertical deformation, and then has a still confining band, which measures which provides also confining pressure to the sample and also measures the confining strain, sorry. So from the test we have, this image shows the soil or the subgrade material, and then the gauge at the bottom after being tested, and we'll look at a few results from this test. So the stress applied for the test was about 60 kilopascals, and the frequency about 5 hertz. What we did was to vary the moisture content of the subgrade materials, and then based on the calibration that we did with the PVC beam, which had a correlation between the strain and then the voltage, we used one of the equations which was at room temperature, because this test was conducted at room temperature, and based on this we just used a simple model to estimate the modulus, which depends on the stress applied, the strain, which has been estimated from the voltages obtained from the sensors, and then multiplied by a calibration factor, which is the quotient of the strain from the subgrade and then the strain from the piezo, as we did in the finite element analysis.
Rufus, you will have to conclude very soon.
Okay. Yeah.
To remain in the time.
Yeah. So we could see that from this is the resilient modulus from the subgrade, and then the back calculated or the estimated modulus from the gauge is in the red, which is known as the PEX. So for 12% moisture content, you could see that you have similar trends occurring from the residual modulus from the equipment and then the sensor, and similar occurs at 15%. So for the lab trials or for the pavement trials, we try to install this just to see how easy it will be to install the sensors, and they are wired. So we try to install that in a pavement test facility in the subgrade, and then also in under the self-healing trial, project trial, we try to install this in the sub base, which is a very new. We for the previous experiments we've been using the subgrade, but now we try to see how we could retrofit this in the sub base. So these are just a few images from the trial in London, where the sensors has been installed. So a core hole was just the asphalt was cored, and then the sensors were installed at the bottom backfilled, and then the data was being collected. But in conclusion, I'll say that reliable readings so far have been obtained from the gauge and could be used to back calculate the trackbed stiffness or the pavement moduli. And if we are able to equip the sensor with the wireless technology, we could collect data wirelessly, and then we could help improve track reliability and maintenance, reduce maintenance costs. Also, for future work, because I'm still working on the PhD, future work is to work currently on different unbound materials, just like the sub base, because for previous experiments I've been using the sub grid, and I'll also validate these sensors and calibrate them using the results I obtained from the field trials, and also a railway test facility, which is coming up in a few months' time. And then also at the end, we should be able to develop a pavement deterioration model from the data collected. And I'd like to thank you for your time and thank the opinion. Thank you.
Thank you very much, Rufus. What's remaining here for your PhD? Already a lot of results, so congratulations for that.
Thank you. Thank you.
So if you can stay connected for some questions maybe at the end of the session. Thank you. And now we are moving to the third presentation. This one will be made by a young researcher, Davide Presti, who is now associate professor at the University of Palermo. And the presentation will be on smart and sustainable solutions for road and airport pavements. So, Davide, the floor is yours. I don't know if you are talking, but maybe your mic is off. Or you're not here.
Yeah, Simone, I'm not here. I'm just having some difficulties. So just let me share it and come back to you. Can you see my screen?
Yes.
Okay, so I just need to put it on it. Well, I know we're a little bit ahead of time, so I'll try to be as quick as possible. So we are in a session that talks about how we can basically conceive smart pavement. And for pavement, we mean road pavement, but also railways, airports, anything that we can pave in this planet. And with this project, we try to basically trial a very innovative sensor that I'm going to introduce, that was developed by Nizar Langev at the Michigan State University, and in collaboration with really many people here. There is me, but there is Nizar, Karim, there is also Gordon, Nick, Juliette, Mario Manosalvas, who is our fellow that put us all together, trying to basically use this sensor to develop what we call the live lab. So a road pavement that, as Natasha showed before and as Rufus showed with for the railway, it's a pavement that can provide data on its structural health, basically. The reason of this is to improve what we currently do in terms of maintenance, mainly by allowing preventive maintenance that we can undertake by building models that are based on data that come directly from the road. So this is already something that is going on in some other, still in infrastructure, is for bridges, but it's other type of components. Sorry, can you see my screen? Maybe not. Sorry,
Yes,
just
we can see your screen.
Just a second. I just pressed a button that I shouldn't. So this technology I was saying is already implemented in some bridges in the States, particularly one in Michigan, where there are thousands of this type of sensor that I'm going to show you. And the sensor has some peculiarities that I would like to underline in the next slide. Just here, I want to say that what we're trying to do is to have a cloud of points that comes from an infrastructure component that comes with information. So it's a really big amount of data, if it's not engineered well, that we need to use to then undertake decision making. For road pavements, what is the current limits? Well, we usually use this type of sensor that are H-shape because they actually can be fixed better when you put the asphalt. But there is no really other reason to have this shape. We can even change the shape. But the limit is not really the shape. It's more that they usually have a high initial cost. We are around €1,000. Different providers, so not all the data are actually could possibly be used in the same way, even though they are usually strain gauges. So we usually measure strain. This solution are wired, and something can happen in the wire, and we don't really want to dig the pavement to fix it. And they come with usually not an easy installation. I mentioned before about the shape, and usually low survivability. So if we need to use it for continuous monitoring, we need something that actually lasts for a long time. The wireless piezo floating gate technology is the technology that Nissan have developed. It's something that goes beyond strain gauges because it's not engineered to measure strain that usually is affected by a different type of load of different type of weather condition. But this type of sensor has the capability of basically measuring the energy needed to deform the sensor itself. So the sensor is this membrane here, which is a piezoelectric membrane, and it has the ability of, again, measuring the energy of its deformation. But at the same time, it gets the energy, the power to actually do the measurement through the passing by of the vehicle. So every time there is an impulse on this membrane, some electrical circuit closes, and this element creates energy that is going to power the electronics for storing the data, and possibly also, if we want to use a wireless communication, a wireless battery. So it's not a lot of energy, but it's enough energy to power this type of elements. This sensor has also the great advantage that if it's produced in mass production, it can cost up to $10, 10 euro. And because it's packaged with resins, it showed to have very high survivability. And at the same time, it's not only made to have a wireless connection and basically battery-less connection, because you don't need to store the energy. It comes always from the vehicle passing by. It has been engineered also to basically store data and give data to the manager only when it's inquired. So you have a continuous storage of data that actually subscribes the data overscribe the data all the time, so to use as less memory as possible. And this diminishes the amount of data. But at the same time, it's not a continuous monitoring, but it's always by inquiry. And this diminishes, again, the amount of data we need to have. And we can just store this data on our computer to do eventually a series of data. I hope this gives a good overview of the sensor. So basically, the vehicle passes over the sensors. There are some electrical impulses that then are analyzed directly or from the sensor or from whoever is going to analyze the data to produce some probability density function that then we will use for decision making. I'm not going into this level of detail, just going to show you that there are 7 levels of information that we can have based on the type of load that passed by. So let's say that we can have very high vehicles that are gonna give this type of information, and very fast and possibly light vehicles, they can have this type of information, and then something in between. Now, we wanted to validate this type of sensor to be used in pavement, and we use the opportunity of a previous project, which is called biopavation, where we install several mixture of different type of mixture. Here you can see there are 4 types of mixture, but really I don't want to go in this detail. What I wanted to show you is that for this 4 type of mixture, we did some visual assessment of what is the creation of cracking, something like that. So we measure for each material how big was the extent of cracks that were being created, over, I think, 1 year testing. Maybe for the fatigue one it was only 6 months, but over a certain amount of period. And we recorded the extent of cracking, and we see what was the amount of loads to actually see the failure. And some of the mixes didn't even fail, but the one that failed, that was actually the standard one, it fell at 900,000 passages of the wheels. Now, keep in mind this number. So we can see that after 900,000 passages, we see a big amount of cracks in that pavement, and possibly that will allow us to replace the surface. Now, what we want to do is to instrument the pavement so that we can have several informations to not necessarily use the visual assessment, but to have something for predictive maintenance. So to intervene before the cracks appear on the surface. And that's what we did. And we installed several types of sensors, and some of these are the one that I show you. So we compare more classical sensor like the one that Natasha showed us before with this innovative one, with actually this one. We realized that despite having different type of information, we actually have very similar trend that I'm not showing here. What I wanted to show here, though, is that thanks to this innovative sensor, the wireless piezo floating gate sensor, this is the same experiment we showed you before. At 900,000 passages, we certainly have all the gates that were the one that I showed you before, the different type of information that provide us already some data that could allow us to think that there is a major damage happening, which is this part here where we consider it being the damage visible surface. But we have also a very great amount of information that are related to the different gates of the sensor that could possibly be used for predictive maintenance. So to identify damage initiation rather than the propagation of the crack and so on. So there is where we would like to work more, and where we actually try to work more to develop some models. And the idea, the vision, is that we could use the sensor as was shown before from Natasha, and also with the sensor that the Rufus is developed, to have live laboratories, so roads that are equipped with low-cost sensors that can provide data, that we can send through different type of means, the internet or whatever we use, to highway managers so that we can optimize our maintenance schedule. I think that's it for me, Simon. Thanks for the attention.
Thank you, Davide, for your presentation. So we will finish this second session with a presentation dealing with nanosensor technology for road pavements, and I will do this presentation. So let me share my screen.
Well, I can introduce a little bit, Simon.
If you want.
Simon Pouget is the Director of Research and Development at EIFFAGE, which is a contractor, but beyond the contractor, really. They're really involved in research and development for transport infrastructure and road pavement in particular. And Simon, together with the other part of the team, supervised Maria, which was the fellow that worked on this project that Simon is now showing us.
Yes.
If he managed to
yes,
I
try to. Okay. Is it okay?
Perfect.
Okay. So I will be quick because a lot of things have already been explained. So this work was done during the PhD of Maria Barriera. So unfortunately, she wasn't able to attend today. She was supervised during her PhD by Dr. Bérangère Lemontal from the University Gustave Eiffel. And with she was supervised by myself as well in EIFFAGE. So I won't take too much time for that, but of course there is a big issue to maintain roads, pavements, infrastructures in general, because there are big issues regarding transportation of people, of goods, so that's why we need to develop solutions to better maintain all the infrastructures we have. It's the case here in Europe as an example, but of course it's the case everywhere in the world. The road is in general the main vector for economic developments and things like that. So it's a very important. When you take a road pavement like this, you can plot the pavement conditions with time, and you start with the excellent conditions to very poor conditions with time if you don't do any treatments or maintenance operations on the pavements. And of course, the idea is to maintain a quite good condition for the road by applying or by doing preventive maintenance treatments on the pavements, and also to decrease the cost of these preventive treatments. So to do that, there are different solutions. Of course, you can use conventional systems, visual inspections, as Davide already said. You can use monitoring devices on top of the pavements, like FWD or deflectometers or things like that. But you can also use, and it's compatible, both are compatible, you can use as well embedded technologies to have remote and continuous monitoring of your infrastructure with no traffic disruption. So that's also an advantage of this technology. And with that, you can be able to propose adaptive maintenance plans for your pavements. So the objectives and of Maria's PhD was prove the feasibility of embedded pavement monitoring. So there were different topics in SMARTI on this part, and to provide high performance, low intrusiveness technology. And I will maybe go more into details on this part. So we can split these two main objectives in different ones. So to propose a methodology for sensor data interpretation to detect the occurrence of damage in road pavements, to propose a methodology to track this evolution of the pavement conditions, and to investigate the benefits of using carbon nanomaterials-based strain sensor for pavement monitoring as well. So Davide already gave some examples, but we took exactly the same experiments that was done during the bioreprevention project. And for the different mixes, we try to plot on this graph the evolution of damage detected on this different section using different technologies. So the first one technology is the visual inspection. So as Davide said, we observed crack, the appearing of cracks at around 1 million cycles or 1 million passages of load. We observed more or less the same thing with Benkelman beam deflection and FWD deflection. So we detect the defect at almost the same number of cycles. And regarding instrumentation, so in this case, it was conventional strain gauges. We see that we observed finally the apparition of defects a long time before the appearing of cracks at top of the pavement. So it's a very interesting technology, and we have good agreement between what we observed with the gauges and what we observed with the different other solutions. So embedded strain sensor is a good option for earlier detection of damage occurrence and for preventive maintenance. I think it's or predictive maintenance. It's very, very important. During our PhD, Maria proposes a procedure to take into account temperature influence on strain measurements, because of course an increase in strain in pavements, we can interpret that in different ways. It can be due to damage in the pavement, but it can also be due to an increase in temperature, for example. So it's very important to be able to know what proportion of this increase in strain is due to temperature and what is due to damage in the section. So she proposes a procedure. So I won't go more into details, but with that we are able to correct the slope or the amplitude of strain measured with the temperature, according to the temperature. She also did some calculations just to know what is important to take into account in a back calculation analysis or in a pavement calculations to be able to fit the best to the measurements on a pavement. So, for example, here in this case, we did some measurements on a trial section. So we plot here the measurements from strain gauges. And we start to simulate, to make some calculations with the ViscoRoot software in different conditions. So in this case, we use only elastic behavior for the different layers, bituminous layers and unbounded layers as well. And we see that the correlation is not so good. So we have tension when we have compression on the field, so it's not really good results. We start to introduce viscoelasticity in the behavior of the different asphalt layers, and we see that the results, it's a little bit different, but slightly different, but not good enough. So we try to take into account the interfaces as well. So in this case, we put viscoelastic behavior to the interface, and we see that in this case we have a very good accuracy or precision, and we can simulate with a good approximation what we observe with the measurements. So what we see in this case is the importance to take into account in the back analysis process the impact of the interfaces between layers in the pavements, because it's mainly composed of bituminous emulsion of bitumen, because there is no water anymore after some times. So it's very important to take into account the real behavior of these interfaces in the back calculation process. And finally, Maria, during her PhD, developed a new type of sensors based off nanocarbon material technologies. And so she developed this kind of sensor. So I don't know if you can see the mouse, but she put some drop of carbon nanotubes in this kind of device, and with that she made a lot of things in the lab just to have a calibration process on that. And finally, she put this kind of sensors in a matte kind of materials like this, and we put these mats in accelerated pavement facility in the University Gustave Eiffel in Nantes, called FABAC, and we compared what we obtained with these sensors with conventional strain gauges, and we obtained this kind of results. So here you have the strain obtained with the conventional strain gauges, and here the evolution of the resistance of this nanomaterials sensor, and we see that we have the same tendency. So when we have an increase in strain with the conventional strain gauges, we have an increase in resistance with this nanomaterial sensor. But we also observe some relaxation. So we interpreted that as a rearrangement of the carbon nanotubes in the sensor. So it's a good first step for the development of this kind of sensor, but we need still times to work on this and to be able to have a very final product to use on pavements. So thank you for your attention. And now I think it's time for question. I don't know if we have time for questions. Davide, let me know how do you want to proceed?
Well, we are actually, I think questions are always good. So
yes,
at least let's ask for questions from the audience.
Yeah. Do you have any questions?
We are, it's okay, we are a bit behind.
Yes. Maybe, yes, we'll have time later for questions as you want, but there is no question. So I have one for Natasha. I don't know if I can ask, but
no, it's your session, but I think you should, to be honest.
Okay.
Yeah.
So Natasha, I have a question for you. I would like to know, how do you characterize the traffic load in real traffic conditions? Because if you want to make some monitoring with the geophones or other sensors, you need to have some information about the traffic on top of the pavements. And how do you do that?
Yeah, actually, this was like this was not in the initial goals that we did, but actually after the analysis of the data, and we were trying to calculate the moduli as well as like model the pavement, and I'm not sure if I can share my presentation. Maybe in another presentation I can be able to present clearly, because there are several steps in which we were, because first we selected a certain type of signal, and then we calculated the model response with Alize in terms of certain reference load, which is around 44 tons. And we compared that reference load with the results that we received from the sensors. So what we had, maybe if I can share my presentation to be much
Yes.
clearer.
Yes.
Can you see the slide?
No.
Not yet. Because maybe you are an attendant. No.
Now?
Yes,
Yes,
now we
it's
can.
okay. Yeah.
Yeah, so this was the approach. So we had limited the signals to just the T2, S3 types of signals. And then we had calculated the model response with the ELISE. And this was just in terms of 44 tons load. And the comparison was with the representative signal, just the signals obtained with the geophones, and we adjust the modulus of the model signal in the obtained with the ELISE under just for the 6.5, like the first how do I say it, the first signal peak, which is under 6.5 tons. So we were just changing the modulus in terms of the first peak, and then we adjusted the modulus of the loads of the rear axles in ELISE in order to adjust or better fit the calculated measured response with the calculated response of the ELISE. So it's like basically more like the back calculation optimization. So we were trying to fit the model response with the calculator response in order to find the loads. So this was like the estimation. It was not the clear load, but it was like an estimation of the load that we can receive from this kind of.
But in this case,
signals.
I think if you use the sensor for road monitoring, you can't use it for traffic characterization. So because you have to know either your traffic load or your load on top of the pavement, either your pavement conditions, but you can't. I'm not sure to understand. You can't have information on both traffic condition and road pavement condition as well with the same sensor, I think.
At least we were able to have like an estimate. So it was just to have a rough idea about how much we can gain from the signals that we have. So it was not like an accurate result, but like an estimate about how much we can get.
Thank you.
Should we go on a break, Simon?
Okay, let's have a break.
Perfect. So if I'm not wrong, the next one should be a 50-50. So which is in 5 minutes, more or less. So Simon, thank you very much for sharing this and for all you've done in the project, really. EIFFAGE has been an incredible partner.
Thank you to you, Davide.